Okay. Thank you very much. Good afternoon, ladies and gentlemen. I will talk now a little bit about the nuclear accidents which happened in the Chernobyl nuclear power plant and in the Fukushima Daiichi nuclear power station. Let us remind the releases to the terrestrial environment. We have here Chernobyl and Fukushima, and the main radionuclides are iodine-131, cesium-134 and 137. Strontium has some relevance in Chernobyl, but little relevance in Fukushima. And xenon-133, there were also large amounts released. Here we have the deposition of cesium-137 in Ukraine, in the Russian Federation, in Belarus, and as a comparison with Fukushima. We see the maximum levels both in Fukushima and in Chernobyl are similar. However, in Chernobyl, a larger area has been affected. So what happened in Chernobyl? This Chernobyl Unit 4 reactor started operation in 1983, and in April 1986 some tests were done on the cooling system in Unit 4. This test went out of control, and there was tried to shut down the facility. However, there was a failure, and some seconds later the reactor ran out of control and exploded. Over a period of 10 days, large amounts of iodine-131, iodine-133, tellurium-132, and cesium-137 have been released. And the releases went on about 10 days until beginning of May. It's the main release in beginning of May. So the emergency measures taken were evacuation, bring people away, application of stable iodine. This is because iodine is readily taken up by the thyroid and may cause pretty high thyroid doses. And if stable iodine is applied in large amounts before the intake of radioactive iodine, then the thyroid is some kind of saturated, and the uptake of radioactive iodine will decline considerably. Then we have food restrictions, decontamination of surfaces, and relocations. This means bringing people away to other areas. So the early measures taken were the morning of 26 April, the town of Pripyat, at a distance of about 3 kilometers from the Chernobyl nuclear power plant. There was the instruction to remain indoors, close the doors and windows, and the dose rates started rising. The next day, dose rates reached 10 millisievert per hour, and the evacuation of 45,000 people started in Pripyat. On the 7th of May, about 100,000 people were evacuated from 76 settlements in a radius of 30 kilometers. And the Chernobyl exclusion zone was established with a radius of 30 kilometers. And this exclusion zone still exists. In 1986, there were about 116,000 people evacuated in total, and also beyond 1986, about 220,000 people were really relocated from areas outside the Chernobyl exclusion zone. So, the measures taken to reduce internal exposures is that the application of stable iodine started already in 26th of April. This was the day of the accident. And it is important that it starts as early as possible. And about more than 5 million people got stable iodine in USSR, but there was obviously no systematic distribution. Food restrictions came into play, in particular restriction on grazing and use of fresh fodder to reduce thyroid doses. This is in principle very effective if it's applied immediately. However, there was, in the former Soviet Union, the implementation of these early countermeasures was a bit delayed. There was also a delayed information of the population about the accident, and so private farmers continued to consume fresh milk and green vegetables, which caused via the pathway pasture cow milk high doses to the thyroid, which could have been avoided. When we look on the areas affected from the Chernobyl accident, this is the deposition in kilobecquerel per square meter, and in total we have affected area of about close to 150,000 square kilometers. Areas with a deposition below 37 kilobecquerel per square meter were considered as not contaminated. So, also in the USSR, there were criteria for remediation were enforced, and there was a change of this criteria with time. The first criteria in 1998 was 100 millisievert as a temporary limit for the average equivalent whole body dose for the period for the first year, from 26 April 86 to 26 April 87. So 100 millisievert for the first year, 30 millisievert for the second year, and 25 millisievert for the fourth year. This is 89 and 90. From 1991, new levels were enforced by Belarus, the Russian Federation, and Ukraine. The USSR separated in 91, and these are one of the states which were formed in this period. So then the intervention level was 1 millisievert per year for both post-emergency situations. And if this level is exceeded, this would mean that remediation measures have to be implemented to reduce this to less than 1 millisievert per year. And 1 millisievert per year has also been chosen by the Japanese government in 2011 as a long-term goal. So this is the affected population groups and doses received. This is what we can see here. There are different groups. These are the workers, operation workers, liquidators, from 1986, 1990. These were people who were involved in cleanup, in collecting fragments, cleaning up the area, etc. And in total there were 530,000 people were involved in this work. We have about 115,000 people evacuated, and more than 200,000 people in areas of strict control with cesium levels larger than 555 kilobecquerel per square meter. This number is equivalent to 15 curies. And 15 curies is the same as 555 kilobecquerel per square meter. And that's why we have this, it's not a round number. And in total, more than 6 million people lived in areas with contaminations higher than 37 kilobecquerel per square meter. Okay, so a huge program was initiated first in the USSR and later on in the three most affected states, Russia, Belarus, and Ukraine, to reduce exposures from radiocesium. This work focused first on residential areas with emphasis given on school, kindergarten, and public buildings. And most was washing buildings with water or special solutions, cleaning of residential areas and roads, or removal of contaminated soil. Agricultural land, there was a wide range of measures, starting with plowing. This means turning the upside down and putting the, if you have a special plow, then you can, so to say, put the surface to a depth of 20 or 30 centimeters, depending on the plow. Then food restrictions were implemented, especially for milk and meat. Then the treatment of pasture, in particular for special for some kind of pastures which were not very intensively managed, and they were then improved by plowing, reseeding, adding K fertilizer, potassium fertilizer, and lime to increase the pH value. Another one is using clean fodder. This is an obvious countermeasure. And also to apply cesium binders. This is a Prussian blue. Prussian blue is a compound that selectively absorbs cesium ions in its crystal, that is, and it's ammonium hexocyanoferrate, and small amounts of this Prussian blue of 10 gram for a cow cause a reduction of a factor of 3 to 5 in milk. So it's a very effective measure. There's one little disadvantage. It is blue. It is a deep blue compound. It is not toxic. No, it's not toxic. It is also used, for example, for humans, if people have incorporated too much cesium-137, maybe workers, they got this Prussian blue, and the excretion is accelerated by a factor of 2. So it's not, this is a stable cyano compound, it's not toxic. However, it looks blue and the pasture look blue, so not all people like it, but it's effective. So, I mean, some of these measures to reduce cesium 137 in crops and animal products are still going on in some areas. Also in some freshwater bodies, we had restriction on drinking water and consumption of freshwater fish. This is easy. Other countermeasures were applied, but they were in general ineffective and not sustainable. So this is an example of the decontamination of a settlement. You see here cleaning the roof, removing the upper part of the soil, the upper part of the loam. Here you see also everything is a very time-consuming and hard work. Okay, and then let's already come to Fukushima. This happened in 2011. So there was this earthquake in the Pacific Ocean causing a tsunami, causing a huge wave, and this wave touched the shore on the east side of Japan. And so you see here the run-up height of the wave, so it's enormous. And I mean, you all know that 20,000 people died immediately as a consequence of the tsunami a bit north of the Fukushima area. The tsunami, or this wave, caused the flooding of the reactor building. After the earthquake, the reactor was shut down. However, when the backup diesels were flooded and they stopped working, and so there was no longer cooling of the reactor. External power was not available because there was a damage of the infrastructure, and this caused the heating up of the reactor core. And so the release of radionuclides started. This is the air concentration close to the Fukushima nuclear power station, and this is cesium 11 March. This is the activity per cubic meter. You have in the beginning high releases, and they go on for some time. The comatose rates at the Fukushima nuclear power plant levels are, those rates are 100 microsievert per hour, up to 10,000. So it was a severe release. If you look at comatose rates, the highest comatose rate was outside 20 kilometers, was about 170 microsievert per hour on 17th of March in this place. This is these are some this is the comatose rate at different places in around different places of Japan. Okay, so which protective actions were taken for the public? First of all, evacuation. This means the rapid and temporary removal of people from an area to avoid or reduce short-term radiation exposure. Sheltering. This is a short-term use of buildings for protection. This means people are recommended to stay indoors, not to leave the house. In relocation, this is a non-urgent removal of people to avoid long-term doses. And this evacuation started very quick. On the 11th of March, we had the earthquake was in the afternoon. And in the evening, nuclear emergency was declared. And 9 o'clock in the evening, there's an instruction was given for evacuation within a distance of over 2 kilometers. And an hour later, evacuation within 2 to 3 kilometers and stay indoors within 3 to 10 kilometers. And this continued, so the 20-kilometer zone was evacuated, and the recommendation was given to stay indoors within 20 to 30 kilometers. And on 22 April, there was also a recommendation given to leave the area northwest outside 20 kilometers. And this looks about like that. This is a continuously increasing area where people were recommended to leave or had to leave. And here, interesting, this is this 20 kilometers zone. And then there's also outside this one track which goes also outside to the northwest. This is this area. That is on 30th of June. And here are, this is from 90, yeah. So this is evacuated. Here people should be prepared to be evacuated. And this is a deliberate evacuation zone. And people could in principle stay, but they are recommended to leave. So there were also some early actions for the public to reduce internal exposure. The measures taken were intake of stable iodine to block the uptake of radioiodine by the thyroid. This is a very effective measure. Then setting a limit for total cesium in food. And in the first year, from March 2011 to March 2012, there was a limit of 500 becquerel per kilogram. And since April 2012, it's about 100 becquerel per kilogram. Monitoring campaigns were started in the field and on the market, and people were provided with information on the activity levels in food. And farmers were recommended to use clean feed if available. I mean, one must say that all these recommendations were quite effective. I mean, and the rapid application of such measures kept the internal exposure to the intake of food really low. This was a real, I would say, a real success. And it was immediately, more or less, implemented. And people also, of course, they were informed, and then they tried to avoid the consumption of products from their garden or from other sources. Okay, this was the first. What you see here is the average dose to a representative person in 2012. This is an estimation which has been done by the IAEA on the basis of data supplied by Japan. And this is the area which has been evacuated. And these are the other areas which for which further on remediation and decontamination activities have been performed. And you see here the doses in 2012 at least, they were not so high. Of course, close to the plant and inside the 20 kilometer zone, doses are higher than 10 millisievert, but in other areas it's something between, it's well below less than 10 millisievert. Interesting is also that here is an area which is not connected to the other areas in Ibaraki and Iwate. This is probably due to the effect of rainfall, and we have seen that rainfall effectively washes out radionuclides from the atmosphere. So, which decontamination and remediation activities were done? First of all, the government of Japan has implemented a reference level for the remediation of land, and we have seen the reference level is a target but not a strict limit. And 1 millisievert per year was selected as a long-term goal, and long-term, according to the dose, the model which has been applied, 1 millisievert per year was equivalent to a dose rate of 0.23 microsievert per hour. This means in the following, all areas above 0.23 microsievert per hour were subject to remediation and decontamination measures. The activity in food was 500 in the first year and 100 in the following years for both cesium. Cesium-134 but cesium-137. In Japan, a lot of tests have been initiated to test remediation measures. For example, for houses, removal of deposit from the roof, gutters and decking, wiping roofs, vacuum sanding, high pressure washing, drying to remove activity from surfaces. In schoolyards, topsoil removal, removal of weed, grass, pasture grass. Is always remove the upper part of the surface, then you remove also part of the activity. Gardenry, mowing, removal of fallen trees, removal of topsoil, high pressure washing, bearing of fruit. In the farmlands, tillering reversal, I mean, this is something like plowing, topsoil removal, soil treatment. This was in particular enhanced application of enhanced levels of potassium. Soil hardening, this means applying a special compound on the top of the soil to make it crusty and then try to remove this crust. This is a measure to reduce also the amount of soil that has to be removed to have an success. Yeah. So this is what you can in principle do. And similar things were also done after the Chernobyl accident, maybe with different techniques, etc., with different equipment, but you cannot in principle do much more than that. And here are some pictures: removing soil, vacuum cleaning, wiping roofs, with a vacuum cleaner, wiping surfaces, washing houses, removing surfaces. And this looked then like, for example, like that. This is before the work. And after the work, vegetation was removed, as well as here, everything was cleaned. Same as here, removing most part, everything, it looks cleaner. However, I mean, this also caused some challenge with regard to the storage of all this material which has been removed from the gardens, from the fields, from the arable land, etc. So in total, about 20 million cubic meters of waste were generated in about 1,000 storage sites. And these storage sites look like that. These are all flexible containers made from kind of plastic, and they were stored in many places around in the Fukushima prefecture. Meanwhile, an activity has started to remove all these plastic bags, and they are now put into an interim storage site which has been established or constructed close to the nuclear power plant, I think in a distance of 3 to 4 kilometers. And the main components of that is soil, debris, I mean vegetation, branches, all kind of things. And if you look at the success, this is a reduction of dose rate in the city of the Fukushima prefecture. We have here residential areas, farmland, forests close to residential areas, and roads. The blue is before decontamination. The dose rate before decontamination. Yellow after decontamination. And then the result of post-monitoring, post-decontamination monitoring is a yellow, is a green one. So in all cases you see a reduction by a factor of 1.6, 1.5, 1.3, something like that. There are no miracles, but in any case, for all these things, for all these places, those rates could be reduced by about 25 to 40%. And it's also important to see that in the residential areas where people live and people stay, the effectiveness was highest. Another really big task was the systematic monitoring of locally grown rice. The Fukushima prefecture has set up a number of facilities which monitored every bag of rice which was produced and should be sold in the Fukushima prefecture. This was a real little factory. Here is the rice bags come here. Here is a detector. The measurement time is 30 seconds or a minute. And then here they are repacked, reconfigured. And then everything got a label. And due to the short measurement time, measurement has some uncertainty. So the limit is 100 becquerel per kilogram. To take account of the uncertainties of the measurement, any bag with a result of higher than 60 becquerel per kilogram was sorted out. I mean, if you look at the effect of the overall effectiveness of countermeasures, I mean, the effective measure will reduce the surface contamination and reduce the intake of activity. This is restriction of food intake of crazy animals, modification of the agricultural practice, in particular in the Fukushima case, additional potassium fertilizer, and also to provide information for people on foods to avoid. From the Chernobyl and Fukushima experience, the dose reduction achieved for external exposure is between 10 and 50%. In following Chernobyl, it is due to these measures, 30% of the collective ingestion dose could be avoided. Collective means the doses integrated over all the population. So this is not an individual reduction, but a collective reduction. And in Fukushima, the ingestion doses were largely avoided due to a strict monitoring of food and restrictions. And also, I think Japanese people are very, very careful, and so there were also some measures which we call self-implemented countermeasures, just to avoid food which could have enhanced levels of cesium. Even this is below the limit. Finally, I would like to make a little comparison between Fukushima and Chernobyl regarding the iodine doses. Iodine has a half-life of 8 days, so it is relevant for the first period only. But I would like to make this comparison because it nicely shows the interaction of thyroid doses due to iodine 131 with living habits and information of the public. First of all, the time of the accident in Fukushima was before the growing period, and in Chernobyl before or during the start of the growing period. I think in Japan, in general, milk consumption is low, whereas in Chernobyl, it is one of the most important foodstuffs. In particular, the rural population, they drink a lot of milk, also because there are a number of private farmers who have a few cows, and so they have access to milk in also high amounts. Food monitoring in Fukushima was very intensive from the very beginning. In Chernobyl, it was less intensive in the very beginning. It started slowly. Another point, the degree of self-supply. I mean, the fraction of food that people produce by their own is low in the Fukushima case, but was high and to very high in the Chernobyl case. Then the information of the public was fast, whereas in Chernobyl it was delayed. And by the end of the day, all these factors come up that the thyroid dose due to ingestion was relatively low in Fukushima, or nearly very low, but was pretty high following Chernobyl. I mean, one has to be aware. Chernobyl happened in 1986. This was the pre-internet period. News were distributed relatively slow, and under the political system of the USSR, it was even more slow. And Fukushima, we had already the internet. It was a more open society. So this information part is essential, but there are reasons for that. I mean, it is as it is, and so this causes this different level of thyroid exposures. Okay. Let me give again some long-term aspects of cesium in the environment. If we look at the long-term processes now in the terrestrial environment, we have the radiocesium in soil, we have uptake by plants, and 2 agricultural products. We have also from soil to resuspension, it goes to air, and it's redeposited on plant. Then we have, this is a kind of a circle, resuspension deposition. And part of it can be inhaled. From soil we have water erosion that goes to bottles, ditches, and sewers, or to rivers, lakes, and ponds. And then we come to the next slide, which deals with the freshwater environment. For the environment, we have surface runoff. This goes to irrigation ponds or to rivers and lakes. And so we have, due to surface runoff, a continuous input of radiocesium to water bodies. And there we can have a transfer to crops, to external exposure during farming, and here consumption of fish, or external exposure from sediments. So the story is not at the end, it still continues, but as we will see, on very low rates. If you look for the long-term behavior of cesium, we have touched this point also in the previous presentation. There's root uptake, resuspension, and erosion, and it leads to a continuous, to a low but continuous redistribution of radionuclides. However, the related migration rates are low. For example, the uptake from soil usually is not more than 0.01% per year, which is transferred from the soil to the crop. And this has also to be seen, so this means the removal of cesium with the crop is very low, and this can be compared against the decay rate of cesium-137, which is 2.3% per year. So this is by far the most important process for the decline of cesium in soil. The same is with the resuspension. It is a continuous process, but also less than 0.1% are removed per year. Water erosion is a bit more difficult because it largely depends on the topography. It is insignificant on a regional scale because it will be removed from one place and it will accumulate downhill on another place. But it could have some local relevance, and it might accumulate in some puddles or ditches or gutters. This may occur, and this may cause locally enhanced dose rates compared to other areas in the settlement. When we look at the countermeasures taken in freshwater systems, they were first of all to reduce transfer of radiocesium from irrigation water to crops. The measures taken were applied to rivers and lakes, reducing sediment inflow, and to facilitate sediment deposition in dams. In the dam, it is on the water, and nobody is really affected. For irrigation ponds was reducing the sediment outflow and removing contaminated bottom sediments and enhanced applications of fertilizer. However, this manipulating sediments is difficult, it's time consuming, it is also costly, and sediments will continue to be to flow into an irrigation pond, for example. The reduction of radiocesium intake by fish in rivers and lakes was in particular food restrictions. No fish consumption anymore, at least for a limited period of time. Also application of potassium in lakes. However, this is also difficult. This was also done after the Chernobyl accident. And to reduce external exposure in rivers and lakes, people stay on the shoreline for fishermen, etc. This is removing riverbed sediments or have flood controls to avoid distribution of sediments. In irrigation ponds, removal of sediments and covering excavated sediments. I mean, everything, the activity concentration sediments is pretty high, can be very high. So a lot of the things are linked to handling of sediments. It always reduced local activity concentrations and local dose rate, but the overall impact to the dose to people is relatively little. So now here's something, I will show some slides where I have given the heading, "The Trend is Your Friend." And this means that we could observe a continuous decline of activities and dose rates of cesium in suspended sediments, air dose rate of cesium suspended in water. And as we have seen before, this decline is faster than the natural decay only. And it is due to migration in deeper parts of the soil, and then the radiation is attenuated by the overlaying soil. We have also a strong fixation of cesium-137 by clay, and this causes a reduced uptake of cesium from soil. And what we see is also everything is more or less consistent with global experience. I mean, one example is, for example, is here the Fukushima prefecture with the contaminated areas, the evacuated zone, and the other zones. The message of this figure is just, I mean, the red and the yellow parts represent the contaminated areas, and we see that these red and yellow areas shrink considerably over 5 years, and this process continues. This is from 2016. Now we have more than 3 years more, and though this area becomes smaller and smaller, even if nothing is done. We see here also the suspended sediment of cesium in water. Inside, this is number 1 and 2, and outside, number 6 of the special decontamination area. I don't want to go into much detail, but in all cases we see that there is a continuous decline of cesium in water, and we can also see here in this period there was decontamination measures were introduced, and this caused an accelerated decline of this suspended cesium-137 in water. Here we have the natural decay of cesium, cesium in suspended matter of rivers of the Fukushima prefecture, also a continuous decline in suspended matter. So the trend is really the friend. And that's cesium in seawater, taken from this book. Similar, these are different places of sites in the waters around Japan. And also there's a rapid decline, and then it continues to decrease. This is cesium in seawater in fish. Here you see some, this is a fish, zooplankton, sand layers are the grosses, and the seawater is this part. But from this figure it seems that the decline in seawater is faster than the decline in fish. But in any case, it continues to decrease. And here is the decline of air dose rate in a decontaminated and control area. This is a decontaminated area, and this is the control area, and both, I mean, here you see the effect of the decontamination, and in both cases the decline continues also in this period for both the decontaminated and for the control area. Okay, that's all.